Okay, yet another concave mirror, and I'm not going to do the cases where the object is right at the center of curvature or right at the focal point. You can construct the rays and see what happens, and I don't want to spoil it for you, at least not right now, but you just follow the rules. Now, if you're at the center of curvature, you can't use the ray that goes through the center of curvature, because you would go straight down through the body of the arrow, and there's no mirror down there, and the arrow's in the way anyway. If you're at the focal point, you can't use the ray that goes from the tip of the arrow through the focal point and then to the mirror, because there ain't no mirror. That's, not very good grammar, but it gets the point across. So you have to use the other two rays. You have to use the one that goes parallel and then through the focal point. Now, the ray that goes from the tip of the arrow through the center of curvature goes on that way. So you're going to do like I showed you in the last one, where you line up your straight edge here, and at the tip of the arrow, go straight to the mirror, straight back. I guess I did show you how to do that. So what I want you to do, or what I want to do next, is what happens when the object is in between the focal point and the mirror. Well, let's say we've got it right here, like that. Well, we can use the ray from the center of curvature to the arrow and back along itself. I've been drawing that particular ray in red, not that it actually matters, but just sticking with it back along itself. Draw a nice little arrow. Now, I can't draw a ray from the tip of the arrow through the focal point and then reflecting off the mirror, because the focal point's on the wrong side. I can, however, do the same trick, if you want to call it a trick, I don't think it really is, of drawing a ray from the focal point to the tip of the arrow and then on to the mirror. So that would be something like, is it going to be in the right spot? Yeah, close enough. That will be like that. Now that hits the mirror right here, and since it came from the focal point, just a teeny bit above that line, it's going to be reflected parallel. Now, there's not really light traveling from here to here. You can leave that blank, it really doesn't matter. The actual physical light starts here, follows this path. We had to use this to figure out the line along which the light will travel. Travels along this line to the mirror and reflects off the mirror parallel to the principal axis. Now, if you notice, these are getting further apart as they go away from the mirror. So our image is not going to exist on the left side of the mirror. The reflected rays do not actually physically cross. So, what? Huh? Well, how is there any, what, huh? So what happens is our eye out here, great big eye, eyes are awesome. I can't draw them particularly well. Here's your pupil, ... right? You can put eyelashes on if you really want to. I don't. Your eye takes this ray of light and it assumes it was going backwards along this path forever. Same thing with this ray of light. Hits your eye, even though I didn't draw it as though it did. Hits your eye, and your eye reconstructs its path as going backwards along this line forever and ever. And so what happens is in order to locate the image, we take the reflected rays, the one that came off the mirror, and we trace them. And we did this, you should have done the ray tracing practice lab already. It's the same basic idea. We take this reflected ray and trace it back past the mirror. And then the same thing with this ray from the center of curvature. Trace it back, and again, I'm using the reflected rays. I'm not tracing this green from the arrow back. I'm tracing the reflected ray back. And where they cross, just barely on the paper there, that's coincidence, I did not plan that, is where my image is going to be. Now, a lot of times what I will do is I will actually dash these lines to represent that there isn't actually any light physically traveling behind the mirror. Because if there were, it wouldn't be a mirror. It would be a clear pane of glass, which is a different thing entirely. So our object would be out here. Now you can see already it's bigger than the object. Excuse me, this is our image, not our object. Again, where the rays cross is the tip of the arrow. The base of the arrow is on the principal axis. And there's ways to prove that. The way to prove it is that you would, easiest way to prove it, I suppose, you would create something like this. Put a circle at the end. Where's the image of that circle? Actually, you would do, put the tip. And so the tip of it would be, the tip of the circle would be roughly there, and it'd be like that, and crosses the principal axis right there. You can figure it out that way. Now, you can use the third ray. You can use the ray, I've been drawing it in blue, that comes from the tip of the arrow parallel to the principal axis, like that. Okay? And this ray follows the same rule as always. It's going to go through the focal point. Now, these are hypothetical rays. We've chosen these not because they're important physically in constructing the image, but because they tell us the path of light. And if you notice here, it goes through the arrow before it goes through the focal point. So in the real world, it would be blocked. You wouldn't have that ray. It doesn't matter because we're using these rays in a theoretical sense to predict where the actual image is going to be. And so, there we go, like that. Extend this back. You can do it solid or dashed, or both. You can see how I did the solid and then put the dashed marks over it. And this is a little different. Let's see, that didn't come out quite the way. There we go. Let's draw that a little darker. Now you can see here the red and the blue crossed in a fair amount closer. Somewhere in here. And the blue and the green crossed out here. Why is that? Well, because of teeny little differences in exactly which part of the arrow. If you look, this red line is actually a little bit lower on the arrow than the green or the blue. So maybe this is probably a better approximation of the image. Also, just really minor misalignments in the angles and that sort of thing can really make big differences in image locations, because when you have real small, relatively small angles like this, even a teeny bit, half a degree out of 40 degrees is a much less proportional difference than half a degree out of 10 degrees. So that's kind of what's going on there. in any case, you can see all of these images are right side up. So that would be upright, or if you're old school, you would call it erect. Now, these images are behind the mirror. The light does not actually exist here. So these are virtual images, and you can see that these are, in fact, larger than the object. So that's how you work it if you have an object between the center of curvature and, an object between the focal point and the mirror. Here you can see the actual physical system. You can see the object. It's just barely inside the focal length of this particular mirror. One of the things you can see here is that because the object and the image are fairly close together, the image is pretty much the same size vertically as the object. However, you can see that the image is much longer in the horizontal direction. It's a larger arrow than the actual physical object is. So the prediction we came up with using the ray tracing diagram is exactly what we see here with the physical system. That's what you call science.